Welcome to another lesson of transparent physics. In this lesson, we'll continue our series on projectile motion, specifically with examples of a horizontal launch scenario, aka a Tier 1 problem. Our goals for this lesson include working through a Tier 1, aka horizontal launch sample problem, and also I'm going to show you how to use the projectile analysis scaffold introduced in the previous video. First step in solving a problem using the QUIPS problem-solving strategy is Q, read the question. So here it is. Police are called to the scene of an accident where a car drove off the edge of a cliff. The edge of the cliff is level and sits 19.5 meters above the ravine below. The car landed 32 meters from the base of the cliff wall. Help the investigators estimate how fast the car was moving in miles per hour when it went over the cliff. Okay, armed with an overview of the problem, next thing we'll do is we'll work through it trying to use our QUIPS procedures. U is underline the important information, so first sentence is just narrative. Second sentence does notice the shear drop of 19.5 meters, so that's going to be handy. Also kind of tucked in there is the fact that the cliff is level. That tells us that it's going to be a horizontal launch. The car lands 32 meters away from the base of the cliff. Useful. And how fast was the car moving in miles per hour when it went over the cliff? So that tells us what we're looking for, and also reminds us that we're going to ultimately convert the answer to new units before the end of the problem. Next up, quick sketch of the scenario. I'll do my best to draw a level cliff here. Going down like this. Over. Again, it doesn't have to be exactly proportionally correct as long as we have the right idea. So here's our car. The car is launched horizontally off the cliff. And of interest to us is the fact that it then drops down into the canyon, impacts the canyon below, and the information they provide to us to assist us with that is the fact that they tell us the cliff is 19.5 meters tall. They tell us the car lands 32 meters away. And we can assign those things to variables. The vertical drop is going to be dy, displacement in the y direction. It's important to note that the object is falling down. So since the object is falling down, let's make sure we emphasize the fact that that's going to be a negative vertical displacement. In the x direction, we have dx. So we're given both the vertical and horizontal displacements. Just for giggles, I will also specify that as far as initial velocity goes, we don't know the magnitude of the initial velocity, but we do know the angle is 0 degrees. And that's basically all they give us to start with here. So let's fill out the rest of the projectile analysis scaffold and see what we can see in terms of other information. So going through the variables associated with that, we have dy, biy, bfy, g, and t. And then going across horizontally, we have vx. We have dx. So there's quite a bit that we actually know right now. We were given dyi, or dy, as negative 19.5 meters. We were given viy as 0 meters per second because of the idea that it's a horizontal launch. I often advise my students to, if we're not asked for the y velocity on impact and we're not given the y velocity on impact, I'll encourage them to maybe put something like NA in that slot, not applicable. That just avoids the temptation of trying to set the final velocity as 0, because remember, we're looking at it the instant before it hits. So the final velocity is not 0, although sometimes students will put that there and they'll actually end up going down the wrong path for the solution. G is always negative 9.8 meters per second squared. G is free. We don't know the time. We don't know Vx. In fact, Vx is sort of the big unknown here. We don't know the speed it launched off the cliff with. And we do know dx. Dx is 32 meters. So taking a look at this, in order to solve something in the x direction, we would really, it would help us to know the time. Now we don't actually know the time to start with, so this is going to be something that we want to find out, and we don't have information associated with it horizontally. If we knew the time, we could solve the problem right now, because if we take a look at our in the x direction, the formula associated with this, because we know that ax is 0, we can always, in the x direction, I'll jot that down real quick, ax is 0 meters per second squared. You don't have to write that because it's always true, but it doesn't hurt. And we're always going to have access to this equation, dx equals vxt. So if we knew the time to start, the problem we've done. We would just solve it and move on with our lives. But we don't know the time, so we're going to have to appeal to the vertical direction to find out that information. So in the vertical direction, we do have 1, 2, 3 pieces of information, and those are going to help us solve it out. So let's start in the y direction, and let's try to solve for the time. We're going to solve for the time it takes for this object to hit the ground. Okay, so I did cut off the narrative, so my hope is that I wrote everything that's important down for the narrative already, so we don't have to go back and look at the problem itself. So when I'm solving these problems out, sometimes what I like to do is specify whether we're in the x direction or the y direction. So to start with, we are in the y direction. And in the y direction, we can start with what I call the Velma equation. dy equals viyt plus 1/2 gt squared. And because it's a horizontal launch, the advantage of this being a tier 1 problem is that the initial velocity in the y direction is 0, so this whole term disappears, which greatly simplifies the math for our solution. So we have dy equals 1/2 gt squared. We're interested in solving for the time, so when we isolate algebraically for the time, and there's videos abroad in the transparent physics universe that talk about how to do this specifically, but when we isolate for time, we get a value of 2 times dy over g, and all that under a square root. And that's going to give us the value for the time. So when we plug in information to that, we have to be a little bit careful, because this is where we'd get bitten in the back pocket, as they say, if we did not remember the fact that the vertical displacement is negative. So we have 2 times the vertical displacement, which is negative 19.5 meters, and then g is negative 9.80 meters per second squared. So when you plug all that into your calculator, I did that, and I got 1.99 seconds. So what that means is it takes 1.99 seconds for the car to hit the ground after it leaves the cliff. Armed with that information, we can go to the x side and use our equation. Now again, the equation that I wrote, just as a quick review, is really just a simplified version of Velma in the x direction. So we have vxt plus 1/2 axt squared. And in the x direction, as I mentioned, there's no acceleration, so this term drops out, and we're left with that simplified equation. And again, you can always start with this equation with projectile motion, so don't feel like you need to derive it every time. I mean, unless your teacher wants you to. Do what your teacher tells you to. But so we are going to be interested in solving for Vx at this point. So Vx is going to be equal to dx divided by time. So that's 32 meters. divided by 1.99 seconds. And that ends up being, rounding, let's say 16.0 meters per second. Now that is an answer, but it is not the answer because the problem did ask us to solve for that in miles per hour. And actually, now that I'm looking at my solution, it probably would have been a good idea, if they do ask for units, maybe throw the units that they want into your solution when you're setting up the information, because it is easy enough to forget to write that later. You might just think you're done. So 16 meters per second converted to miles per hour. Again, a different lesson for a different time, but 16.0 meters per second. We have 1609 meters per mile and 3,600 seconds per hour. So seconds cancel with seconds, meters cancel with meters, you get miles per hour, and when you do the math, 35.8 miles per hour. So 35.8 miles per hour isn't crazy fast, but definitely faster than you should be driving off the edge of a cliff. And there you have it. You have a horizontally launched projectile, also known as a Tier 1 problem in transparent physics nomenclature. Just general advice, good for any problem, but especially in projectile motion, be careful with your subscripts. They're going to help you assign information to the proper variables. It's very easy to maybe put a vertical velocity where a horizontal velocity goes. Your subscripts will try to act as a bit of a barrier to prevent that from happening. Okay, click the like button if you enjoyed being a crime scene investigator for about 10-15 minutes here. Please consider leaving a comment if you have any questions about the solution strategy I presented. And subscribe if you want to see what's coming next from Transparent Physics and to help the channel grow. Hey, and thanks for watching this lesson. It's nice to talk about the concepts, but I really enjoy working the problems out and seeing how the physics works out in some more realistic scenarios. I hope I've made the prospect of a horizontally launched projectile a little clearer for you on this lesson of Transparent Physics.